A very warm welcome to once again. So, our lecture is based on regular expressions. So, our last lecture, which was based on finite state machines in terms of epsilon NFA, NFA, and DFA as well, and also in last lecture, I introduced you people with regular expressions. So now today we'll go in uh, deep analysis for regular expressions. So let's get started. So what is a regular expression? Basically, if I define a regular expression, so regular expression is basically a set of inputs, a pattern of inputs. Inputs are basically like that alphabet which we provide for to any kind of either it is NFA, either it is DFA or epsilon NFA. So a regular expression is sorting sorting skill for like fundamental languages like Perl, and it is also useful for Lex. Lex is a tool which we will see in the compiler lab, which is known as lexical analyzer generator. So a regular expression is describe like a regular expression to NFA, NFA to DFA, and we can also convert from NFA DFA to NFA and NFA to regular expression as well. So for this concept we have seen already in previous lecture. Now this is the example uh, of regular expressions in compiler design. So this is the state, this is the state, this is the final state, and this is the final state, this is the final state, this is also the final state, final state, final state. So this is less than and this is equal to. Once this pattern is matched, then what will be returned from this graph, transition graph, is relope. Relope is basically a token for less than equal to. LE means less than equals to. Now this for this token, like for this token, it is not equal to. For this token, it is less than, because after less than there is nothing, right? Here we will return an uh, relational operator token for attribute EQ. EQ means equal. Now for this DFA, it is greater than equal to, and uh, it is basically for greater than only. Now this is the example for regular expression. So the following operations we can use for regular for languages that are used for regular expression. The first one is union operation, the second one is concatenation operation, and the third one is clean star. Okay, now this is the definition of a regular expression. So a regular expression is A for some A in alphabet sigma standing for the language A. What does it mean? It means if we have an alphabet A which belongs to sigma, then it will stand for A braces, A close braces. So this will be a language. Now sigma, if I talk about alone sigma, it is a regular expression, but if I convert the sigma into this form, so it will be called a language. Now this is phi. This stand for empty language. Now this is the first important rule. If R1 and R2 are the regular expression, if R1 and R2 are the regular expression, then R1 plus R2 will be a regular expression where the plus operator perform the union between R1 and R2. Now, if R1 and R2 are regular expression, then R1 R2 will be a regular expression where it the R1 and there is no operation between R1 and R2, so this is the concatenation operation. So if R is a regular expression, then R asterisk will be a regular expression. This is called as closure. Now if R is a regular expression, then R open bracket R close bracket will be called as a regular expression, right? Now these are the examples of regular expression. If we have a language like this 001, then this is the regular expression. If we have a language 0 plus 1 0 asterisk, so it basically is nothing. It has the first union operation, then concatenation operation, then closure. Then these are the values, these are the possible patterns which will be following by this language or accepting by this language. So similarly this one. Now this is a very important rule. R is a regular expression if we concatenate sigma, if we concatenate null with R, then it will equal to R. Now if we union for any regular expression R with phi, then it will equal to that particular regular expression, right? So these are the examples and these are the basically rules. These are the rules for regular expression. Now this is the equivalence cycle for regular expression. So if we have a regular expression, then we can obtain a regular expression, NFA from a regular expression, and from an NFA we can obtain a DFA as well. From a DFA, if we apply Hopcroft algorithm, then we can obtain a minimized DFA, and from minimized DFA we can obtain code that will be required for compiler. And further, if we want, then we can also convert from minimized DFA to a regular expression. So everything is connected and everything is equivalent to one another. Now, how can we convert a DFA into a regular expression? So there is a theorem: if L is equals to LA for some DFA A, if A is a DFA, then language accepted by this DFA is equals to L. Then there is a regular expression R such that L is equals to LR. And that there will be a regular expression for language L, which will be equal to L, right? So we can prove this particular theorem in two terms: construction of GNFA. GNFA is generalized NFA or state elimination. So these two methods we have seen in automata theory. We will not bother about it. We will not discuss these two things, but we'll see bit introduction, right? Now how can we convert a DFA to regular expression? So basically if we see a DFA, then a DFA will be looking like this one. A DFA will be looking like this one. These are the states and somehow there will be any input. Then let's suppose this is a DFA, or this is the NFA. Then always a regular expression is in form of inputs, in form of 0 1, or in form of any kind of input, whether it is A comma B, 0 comma 1, 0 comma 1 comma 2. So we need to eliminate these particular states. So if we successfully eliminate these particular state, and we get the inputs in that particular sequence for that follow the union operation as well as concatenation operation as well as closure operation, then we can say we has a regular expression for the following for the given DFA. So we can eliminate the states, right? This is the example. Like if we see this is the DFA, let's suppose this is the DFA. Now this is again a DFA, but what is the difference between these two DFA? Now this is the generalized DFA and this is not the generalized one, because there is we have eliminated we have eliminated some ways or some transitions, and after eliminating some transitions we get like this structure: R11 plus Q1 S asterisk P. What is this? This is basically a kind of regular expression. Now, once we eliminate all the transitions, then the transition will not exist, and after transition will not exist, then state will not be exist. Then finally what we get, we get complete regular expression. Like from here we get this one, so from there we will get a big regular expression for this particular diagram, right? Now, this is the DFA2 regular expression using state elimination. So this is what basically this is a DFA. So here is a RSTU. There are some inputs and there are the states S1 and S2. This S1 is basically initial state and S2 is basically the final state, right? So this is basically the regular expression. How it is get? It is get, there is a loop of R, or we can say here like this, R asterisk plus S U asterisk, then T, then whole asterisk, then SU. Means S is mandatory from S1 to S2, and from S2 to S1 T is mandatory. Why? Because from if we transit from one state to another, definitely we need some input, right? uh, So this is another example. Now, what is difference between these two examples? There is a little difference. There is a 0 comma 1. So now this input can be written as 0 plus 1. 0 comma 1. A comma is indicating the union between 0 and 1, right? So that is how we can able to convert DFA to a regular expression. Now this one is again, what is difference between this diagram and this diagram? So this is basically if we see 0 1 1 0 plus 1, so it is already a regular expression in itself. Now we need to convert this one, so this is in concatenation, so we can write this one is 1 1, and this whole is written as like 0 plus 1 0, 0 plus 1 0, because 0 plus 1 and 0 will getting in the same state. Now further if we reduce this 1, then we can got this answer, 0 plus 1 whole strict 1 1 concatenation 0 plus 1 the whole aspect. So that is how we can convert, we can obtain a regular expression from a given finite automata. Right, these are some examples. Like if we have a regular expression A, then we can describe like this. If we have null, then null will be treated as the initial as well as final, where every input is, where everything is accepted, right? R is equals to 5, R is equals to 5 means there is only a initial state, no final state is there. So in next slide we will see more complex regular expressions. Now these are the more complex regular expression as compared to previous one. R is equal to S plus T. So this is basically the regular expression of for S, and this will be regular expression for T. Now if we concatenate, oh sorry, if we union, then by this way we can go for S, by this way we can go for T, and this is the final state. ST, if there is, this is the S and there is a T, then we can concatenate by taking null between these S and two regular expression. Now R is equals to S asterisk, which means there is a loop and everything is accepted over here. uh, that means initial as well as final, right? So this is basically S. Now there is a closure on S, then for obtaining closure we will add another state before this one, and we will add another state that will be called a final state by using null, and we will go for a transition from this state to this state using null. Now, from a regular expression to NFA, it is again possible in reverse manner. Let's suppose we have a regular expression, then how we can obtain the NFA. So simply A will be concatenated with B, and finally A will be in union, right? Now like this. So this is A, right? This is A, and this is AB. Now this is AB, and finally we need to open the closure. Then how can we open this closure? This is null and this is final state, and let's suppose this is my initial state. Then what we need to do is we need to do like this, in which I learned, which I read in previous previous slide, right? So this is basically the regular expression of finite automata from this regular expression. Now like this can be for AB plus A asterisk. Now this slide talks about the algebraic rule for regular expression. There is L plus M is equals to M plus L. This is called as commutative law. Commutative law. Associative means L plus M whole L plus M plus N is equals to L plus whole M plus N. The associative law for concatenation is Lm into N is equals to Lmn. So there is no commutative law for concatenation like Lm is not equal to Ml, because this basically is a pattern, not values like 2 3 is not equal to 3 2, but if we apply the multiplication between these two, then it is equals to, right? So like this, it is a pattern. Lm is a pattern, so Ml is a pattern which doesn't, which never match. Now these are some more identities like L plus phi is equals to phi plus L. This is for union, and this is L concatenation null is equals to null concatenation L. Now phi null L phi is equals to phi, and many more. So these are very important, as well as very easy for you guys. And these are the laws that involve the closure. If we see this one, L closure, then it will always equals to L asterisk or L closure. Now phi closure is equals to null, and null closure is equals to null. L plus is equals to LL asterisk, which means L plus is equals to L asterisk minus what? Null. This does mean L asterisk is equals to L plus uh, L plus null. This is same, and right. So these are the some algebraic laws that completes the definition of closure. So that's it about the regular expression. Now in our next video lecture, we will see the concept of grammars, grammars in the sense of context free grammars, and many more grammars. So we will have one more lecture tomorrow, or possibly day after tomorrow on it. So thank you for today. Thanks.